Okay, welcome to part 2 of this video, in which we look at concurrent forces in 2 dimensions. In part 1, we computed the x and y components of force A and FA and FB, and between finishing part 1 and starting part 2, I've computed the x and y components of FC and FD and drawn them on the screen here. What we want to compute, again, is the resultant, which is the sum of these guys. And so the way we can do this, we can get the x component of F by adding all of the x components of FA, FB, FC, and FD. So we will take these values and add them all up. And that will give us the x component of the resultant force. So let's do that. So we have then minus 48.1 plus 45.3 plus 37.7 minus 44.6, and that gives us negative 9.7. So these guys sum to negative 9.7 pounds. Okay, let's look at the y components. And again, we will sum these guys to get the y component of the resultant. So we have 13.8 plus 21.1 minus 32.8 minus 22.7. And that gives us negative 20.6 pounds. So we have minus 20.6 pounds. Okay, so we can say then that our resultant force is given by this x component times the unit vector in the x direction minus 20.6 pounds times the unit vector in the y direction. So if I were to graph this, I would get something that looks about like this. And you can see that this really does look about like what we expected our answer to be from doing this graphically. So, to summarize, to solve this particular problem where we had to find the resultant, we found the x and y components of each of the forces involved, summed those x and y components, and that gave us the resultant. And that was fun. Now let's suppose that we have a slightly different problem. Okay, suppose that we still know that the magnitude of FA and the magnitude of FD are 50 pounds. We now don't know the magnitude of FB. We know the angle that it will be applied, but we don't know what magnitude it has. And the same for FC. We know which angle, or the angle that it will be applied at, but we don't know its magnitude. And in fact, what we want to do are choose FB and FC to create a resultant force that is 10 pounds, this guy here, in the x direction and 0 pounds in the y direction. Okay, so maybe what we want to do is start accelerating our camera down the field because I don't know, somebody's racing down the field towards the goal line or something like that. So in this case, we want to find what the magnitudes of the vectors are going to be. So how do we do this? Well, we follow essentially the same procedure we just did. We'll express FA, FB, FC, and FD in terms of their components, but FB, the magnitude of this vector, and FC will be unknown. And so these will be two unknowns. It turns out that we'll get an equation for the x direction and an equation for the y direction. Those two equations will allow us to solve for the desired values of FB and FC. So that's where we're headed. I won't compute FA, or the components of FA or FD. Those are the same as in the previous problem. What I do need to do, though, is come up with an expression for FB and FC in terms of their x and y components. So if we look at this, the vector FB will be equal to its magnitude times the cosine of 25 degrees I hat. That's basically projecting the hypotenuse FB onto the x-axis, plus FB sine 25 degrees, j hat. And if I write out what these guys are, whoops, that will be FB times 0.906 I hat plus FB times 0.423 j hat. Okay, so hopefully that makes sense. One thing that I'd like to point out here is that what we're actually doing is we are expressing this vector FB in terms of its magnitude and a unit vector that has the same direction as FB. And this unit vector you quite often will see represented as lambda hat B. So that's what this guy is. And lambda hat B is 0.906 I hat. That's basically this guy. It's also cosine of 25 plus 0.423 j hat. So another way of writing the vector FB is as the magnitude times lambda hat B. Okay, so again, that's a useful concept. Unit vectors are very handy in 3 dimensions, where looking at things geometrically becomes more difficult. Okay, so FC we can write this quickly as this is FC cosine 41 degrees minus FC sine 41 degrees, and this gives us FC times 0.839 I hat minus FC 0.545 j hat. Okay, so we've expressed FB and FC in terms of their x and y components. Let's go to this slide where I've actually rewritten FA and FD and rewritten FB and FC. You can check with the previous picture to make sure I got it all right. Hopefully I did. If I didn't, please point out what I got wrong. So again, we will sum up all of the x components, which you can see is this group of things right here. The thing that makes this different from our previous example is that we don't know what FB or FC is. We're solving for them. So summing up all of the x components, we have minus 48.1 pounds plus 0.906 FB plus 0.755 FC minus 44.6, and we want this resultant force in the x direction to be equal to 10 pounds. So we'll set this equal to 10 pounds. Okay. In the y direction, we have all of these values, and we'll sum them up. We want them to be 0. So we have 13.8 pounds plus 0.423 FB minus 0.656 FC minus 22.7 pounds, and this is equal to 0 pounds. Okay, so we have our two equations and our two unknowns. Again, our unknowns are FB and FC. So let's solve these two equations. You can do this using your favorite method of solving linear equations. I'll just type them in. And we have minus 48.1 plus 0.906, and I'll just call this B because Wolfram Alpha likes that, plus 0.755C, I'll call FCC, minus 44.6, and this is equal to 10. So that's our first equation. Our second equation is 13.8 plus 0.423b minus 0.656c minus 22.7, and this is equal to 0. And Wolfram Alpha shows us all sorts of useful stuff about this, but at the end we get that the solution, FB and FC, FB is going to be 81.1 pounds, rounding to 3 places, and FC is going to be 38.7 pounds. So if we go back to our picture, we can say then that FB needs to be 81.1 pounds, and FC needs to be 38.7 pounds in order to have the resultant of all of these forces be 10 pounds in the x direction. So there you have it. Hopefully this has been useful. We've shown how to break up vectors into their components. We've shown how to add vectors analytically and graphically, and we've shown how to find a resultant if we know all of the vectors, or find magnitudes of vectors if we know what we want the resultant to be. So that concludes this video. Thanks for watching.